This should be the last video related to the final exam review for College Algebra Math 1111, and we're looking at the applications and exponentials of logarithms on page 8 of the review document. And we'll begin with the first question, which says, if $10,000 is deposited into an account that pays 4% compounded quarterly, approximately how much money will be in the account at the end of 12 years? Round your answer to the nearest cent. Well, a couple things here. One, it's talking about interest. And the second thing is I see this Lee word, quarterly, so that lets me know that I should use the general compounding formula, which is A equals P times 1 plus R divided by N raised to the NT power. And so then the first thing I want to do as I begin thinking about this problem is to identify the information that I have. So if I go back and I read through the problem, again, it says $10,000 is deposited. So that's the initial amount, or my principal, which is P in the formula, that pays 4%. The percentage is always your rate of interest. Remember, we need to write that as a decimal, and so we take 4 divided by 100, which becomes 0.04 when we plug it into the formula. Compounded quarterly. Quarterly tells us how many compoundings there are per year, and quarterly means every 3 months, so it occurs 4 times per year. It says approximately how much money, so we're looking for the accumulated amount or the final amount in the account after or at the end of 12 years. So I've identified all of the information, and then it becomes a substitution problem. So I would have $10,000 times 1 plus 4% divided by 4 raised to the 12 times 4 power. And then, guys, really, you need to walk it through, but you can use your calculator to do that. We would begin by dividing, working in the parentheses. We would divide 0.04 by 4, which gives us 1/100th. So you would have 10,000 times 1 plus 0.01 raised to the 48th power. I can do 12 times 4 in my head. Then I need to add what's in the parentheses. I can do that in my head. So I have 10,000 1.01 raised to the 48th power. And then I definitely want to get my calculator. So I'm going to add 1 to 0.01. I want to raise it to the 48th power, which gives me this big long decimal. It becomes 10,000 times 1.612226,078. Then we're going to multiply that by 10,000 equals, and we get $16,122.26. See, it does say round to the nearest cent, so that would be 2 decimal places. So we would have $16,122.26. And I know that when you enter this into the computer system for the final exam, they do not want you to put the dollar sign. So just put the number. The next question is a half-life or a carbon dating. It says carbon-14 is a radioactive substance with a half-life of 5,730 years. If an object known to begin with 2,040 micrograms of carbon-14 now has only 155 micrograms, then how old is the object? Round your answer to 2 decimal places and to remember to use labels. So remember, when we're dealing with half-life problems, we actually use the continuous compounding formula, which is A equals P times E to the RT. And in this problem, if I look at it initially, I'm kind of a little bit at odds, because I know that we start with 240 micrograms and we're going to end with 155, and we're trying to figure out how old, so that's T, but I'm actually also missing R. But I have enough information that really I can find R, so I have to kind of do that first. I have to figure R, which is the rate of decay, or the decay rate. Well, I know that the half-life is 5,730 grams. So if I know I'm going to have half of the material left, and I started, say, with 1 or 100%, and I'm going to have half left, I have E to the R times 5,730 years is how long it's going to take me to have half left. So if I divide both sides by 1, I have 1/2 equals E to the 5,730 R. Then I need to take the natural log of both sides, and this is going to be kind of a really big number. So I have the natural log of 1/2, which you can do on your calculator. It gives me negative 0.69314711806. And that equals 5,730 times R. So if I divide that value by 5,730, it's going to give me the rate of decay for carbon-14. And guys, when it comes up on your calculator, let me show you what it looks like, because it looks pretty funky. Okay, you would have the natural log of 1/2, and then you divide that by 5,730, which is, it looks really weird because be careful, you have this E to the -4 at the end. That means you need to move this decimal back 4 places. So we actually have negative 0.00012, and it's this big long decimal. And they really want us to carry the decimal out with us as we go so we can hang on to it. So there's R. So then once we've found R, and I kind of need a new slide here so I can have some room. Okay, I'm going to move on to a new slide, because then we're going to take these numbers and we're going to plug in using that R value. So I have let me get back to my... We know we're going to end with 155. We started with 240 E, and we have that negative 0.00012 times T. We're trying to figure out how long is it going to take. So then we set about solving this equation for T. So I'm going to divide both sides by 240. So we have 155 divided by 240, which gives us 0.64583 repeating, equals E to the negative 0.00012 times T. Then I need to get rid of the base E. We do that by taking the natural log of both sides. So we're going to take the natural log of 0.64583 repeating, and the natural log of E to the negative 0.00012 times T. Okay, again, the benefit of doing that is on the right side, the natural log and base E will divide out. So we have the natural log of 0.64583 equals negative 0.00012 times t. Well, remember, I'm trying to solve for t. So then I'm going to divide by this big long decimal number. And it's going to get really kind of messy to put all this in your calculator, but I'm going to try to show you here in just a minute. Okay. Whoops, got too many zeros in there. 1, 2, Now, the reason I'm keeping all these decimals is because I happen to know the answer, and that's how they did it when they created the answer for you. So I'm going back to my calculator for a minute, okay? And I'm going to kind of save some things in my calculator as I go. So we had 155 divided by 240. Okay, so there's the natural log of this 0.64583. Okay, before I do that, though, let me go back and let's get the half-life rate of decay again. That was the natural log of 1/2 divided by 5,730. And I'm going to store it. So you can store it if you press store and then alpha A. So I've stored that number in my calculator so I can use it. So then let's go back. Natural log. I need to do the 155 divided by 240. Oops, sorry, I had a mistake there. 155 divided by 240 equals that decimal number. I'm going to take the natural log of that decimal number, and then I want to divide it by the number that I stored. So to get it back, I do second store alpha A, and it pops that big long decimal back in there, and it gives us a value. T is 3,614.29. Now, if you round preliminarily, you'll get a different answer. And so, again, I had the advantage of knowing the answer that the author of these questions had done, and they carried all the decimals with them. So just be careful about that. If you get a value that's a little bit off, it may be that you need to carry out more decimals. Okay, so the answer here is T equals 3,614.29 years. Okay, and I do want you to put in the units, and it's years because if you go back and look at the original question, your half-life was in terms of years. Okay, so then let's move on to the next one. This is a supplemental question. It's another half-life question, and it's about the polonium-210, similar to the ones you saw in example 4 or in module 4. So it says polonium-210 is a radioactive substance with a half-life of 138. So I'm going to underline that as I go. Half-life of 138 days. A nuclear facility is handling 315 grams of polonium-210. Then how many grams of polonium-210 will be left in 350 days? Round your answer to 4 decimal places and remember to use labels. So again, really here we're still using our continuous compounding formula, but initially we have to find the value for R. So again, we know it's the half-life, so we're going to have half of the amount left. If we started with 100%, we're going to have half of it left. Okay, so we would have E to the R times 138 days. Okay, so we would have 1/2 equals E to the 138R. I'm going to take the natural log of both sides. Again, by doing that, what I've accomplished is I've eliminated the R or the E. So I would have the natural log of 1/2 equals 138 by R. And then to get R, I'm going to do the natural log of 1/2 divided by 138. And you can do that on your calculator. Again, you want to try to carry the decimals with you, and it's easier to do that if you save it in the calculator. So we do natural log of 1/2 divided by 138, which is negative 0.00502. Okay, so we have that R is negative 0.00502. Okay, so I'm going to save that value in my calculator. Again, I'm going to tell it to store, which is right above the on button. And then I press the green alpha button and one of the letters. And I use A, which is the math button, directly under the green button. It just makes it easier. Okay, so now that I know the rate of decay, which is R, then I go back and I pick up the numbers from the problem. I'm told that they're handling initially 315 grams. So I have 315 grams. The rate of decay is negative 0.00502. And it's going to be left for 350 days. And we want to know how much is going to be left. So in this scenario, we're actually looking for A. And really at this point, it becomes a calculator problem. You can put it in the calculator just like you see it written there. So let's do that. We have 315 times, and to get E, it's the blue second button, and LN. And we want our rate, so we do recall it. We're going to second, store, I stored it in A, times the 350 days that they're going to hold it. Okay, and you get 54.3036, and they wanted 4 places. So we would say that there are 54.3036 grams of polonium left. And again, they want you to give the units because it says to use labels. And finally, it says Gordon invests $91,000 into a CD compounded quarterly. So I see that Lee word there. Compounded quarterly with an annual interest rate of 5.7%. How much money will he have after 5 years? Round your answer to the nearest cent and provide only a numerical answer. So they don't want you to add in the dollar sign. So again, I see that Lee word, so I know I want to use just the basic old everyday compound interest formula, which is A equals P times 1 plus R divided by N, all raised to the NT power. And again, one of the first things I want to do is try to identify all of the information I have. It says that he deposits $91,000 into an account, compounded quarterly. Again, quarterly is the idea of every 3 months, so that's 4 times per year at 5.70%. Again, remember to change your percentage to a decimal. You take 5.70 divided by 100. You have 0.0570. And it wants to know how much money is Gordon going to have after 5 years. So we're looking for A. So again, it becomes a straight, flat out substitution problem. We would have 91,000 times 1 plus 0.0570 divided by 4 raised to the 4 times 5 power. So again, the first thing we're going to do is the division within the parentheses. 0.0570 divided by 4 is 0.01425 to the 20th power. Add those things inside the parentheses. So we have 1.01425 to the 20th. Then I'm going to definitely get my calculator out. Okay, so I would have 1.01425 raised to the 20th power times 91,000 gives me $120,765.18. Okay, be careful. 176. The 6 next to the 7 is going to bump it up an extra penny. Okay, so we have $120,765.18. Okay, and again, when you write your answer in the computer, they don't really want you to put the dollar sign, although I did write it there, but they don't want you to put it when you enter your answer. It says, provide only a numerical answer. If you add the dollar sign, it'll count it wrong.